Recording. Okay, so the meeting is now recorded and I think we can start. So hello everyone, welcome to episode 43 of Warsaw Quantum Computing Group meetups. Today we have a pleasure to host two great speakers from the Center of Theoretical Physics from the Polish Academy of Sciences, Jan Tuziemski and Filip Maciejewski. They will give a talk about efficient learning and benchmarking of readout noise crosstalk models in near-term quantum devices. So sounds interesting. This meeting is recorded as usually. So hopefully the video will be available on our YouTube channel later. And if you have any questions during the lecture, you are welcome to interrupt. So you can unmute yourself and ask the questions, or you can post your questions on our chat, and then we can ask the questions at the end during the Q&A session. Before we start, we would like to thank our strategic partners for supporting us, Snarto and Cogit. We would also like to thank our honorary partners for helping us in organizing this meetup, advertising this meetup. And I think we can start. So I will now stop sharing my slides. And Jan, I know you will be first. So if you are ready, the Zoom is yours. So first of all, welcome and thank you for accepting our invitation to be the speaker.
Yeah, thanks for having us here. Let me just go to the full screen mode. Can you see the slides?
Yes, I can see at least.
Oh, okay, yeah, that's perfect. Okay, thank you very much. So you know the title of the talk. So this is a joint project done in collaboration with Filip, who will tell you something about it also later, and Asia, Majsak, Oskar Słowik, and our boss Michał Oszmaniec. So we are part of a quantum computing theory group led by Michał, and there are like 3 postdocs. One just joined, so there is no picture of him here. 3 PhD students and some students, and later there will be an advertisement. So if you are looking for a postdoc position, there is one open in the group. So if you would like to join working with us, there is such a possibility. Filip will tell you more about it later. Okay, so now coming back to the main topic of the talk. So today we are going to tell you about current quantum computing devices. So as you may know, there are some of them are available. So for example, you can use this IBM quantum devices. There are also like other providers of those devices like IonQ, Rigetti, and many more. But the state of the art is that those devices are really noisy. So they are affected by noise, there are errors there. And currently we are not able to run like quantum error correction. And this means that basically we need to live with the noise that is present in those devices. On the other hand, people try to understand and find out whether those devices can be useful for something, for some tasks. And we have hopes that this is indeed the case. But this noise present in those devices can kind of destroy potential advantage that they can give. And on the other hand, if you know what is the noise that affects your device, there is a certain set of tools that allows you to improve quality of computations that can be performed on those devices. And those techniques are known as error mitigation. And the difference between error mitigation and error correction is the following. So if you want to use error mitigation, you basically run an algorithm on your noisy device, and you know that like the results that you get are affected by noise. And then in the post-processing stage, you try to remove influence of this noise on your results. And but in most cases, to use those algorithms, you really need to know what kind of noise affects your device. So therefore, it is important to have a way of characterizing noise that affects your device. Okay, and of course, we'll be here. We focus on this gate-based based model of quantum computing. So this is a very schematic kind of picture of how it works. So you prepare your state, then you perform some operations on this state, and these are like quantum gates. And finally, you perform a measurement. And in this talk, we'll be focusing on noise that is kind of that affects this readout process. Of course, this is not the only source of noise in those devices. So you can have like imperfect state preparation and also those gates that you perform on your qubits. They can also be imperfect. But here we will just be talking about this readout noise characterization. Okay, and those errors that are present during the readout process, they are really significant. So if you open some papers on algorithms that have been performed on those devices, and you will look for characteristics of noise, which usually are described there, you will find out that those errors during the readout process are really the most sort of important ones. So here is a picture from this famous quantum supremacy paper by Google from some years ago, and they provide like characterization of the device that they used, and basically the errors related to the readout process are 10 times bigger than the rest of the errors. So for example, like the errors connected to the performance of 2-qubit gates or single-qubit gates. So really this is like this readout process is significant part of noise that affects those current quantum computing devices. Okay, are there any questions here, maybe? If not, I will go.
I don't
yes?
see any questions on our chat. So if you would like to ask any question, please raise your hand.
Yeah, and yeah, okay.
Okay, I think we can go on.
Okay, thanks. So just to give you like a basic understanding what can go wrong when you read out your qubit, let me consider a very simple example. So this is like a single qubit readout process here. So imagine that your device prepared your qubit in the 0th state. So if this readout process would be ideal, what you should find out when you measure your qubit, you should find out the result that corresponds to that state. Yeah. So basically, there will be some measuring device showing you like 0, which means that the qubit was in the state 0. But now there is some noise involved in this process. So there is like a non-zero probability that you will find out that this qubit, that your device will tell you that your qubit is in the other state, so the first state. Yeah. And there are some physical reasons for that. I will not go into details, but please believe me that yeah. So this is this is really the case. Yeah. This can really happen. And of course, the same story holds for the other state of the qubit. So if your device prepared like that, like this, the state 1, let's say, ideal measurement should reveal that state. But again, there is like a non-zero probability that you will like read out your device and you will think that the qubit was in the state 0. And this was like an example for like a single qubit. But of course, like devices that contain like 1 qubit are not so interesting. If you want to do something useful with your device, you need many qubits. So the question is, okay, how does this like generalize to more qubits? And then again, if you like would like to have some scheme, if you have your device, then this kind of lambda, this is like a schematic representation of noise that affects your readout process. So if you go to many qubits, you can find that those errors start to be correlated. So there is like a crosstalk. So this readout errors there will be correlations in those readout errors. So for many qubits, this story starts to become more complex. And again, just to provide you with a very simple example, so imagine that you have like 4 qubits and your device prepared it in this like O0 state. So again, this ideal measurement, if there would be no noise, should reveal that this was the state that was prepared by the device. But again, now there are like some error, that there are like error probabilities that you will find out that the state, that you will find out that this is some other state. So I didn't like write all of them, but in total you will have like 16 elements. Like you will need to specify like 16 transition probabilities of that kind for like 4 qubits. And you may already see what's going on here. So if you go to many qubits now, and you want to kind of write this relation between your noisy probability distribution that you observe and the ideal probability distribution that you should have observed if there was no noise in your device, there is like a matrix lambda that connects the two. And the problem is that for this matrix scales exponentially with the growing number of qubits. So the more qubits you have for a generic noise, let's say model, you will need to specify like number of probabilities that is exponential in the number of qubits. And this means that characterization of such a noise process becomes infeasible for large devices. But this is really what we are interested in. Like, we are interested in characterizing noise on those large devices. So the question is, like, can we do something about this? And just to like highlight the solution, so we'll consider like local models of noise, and I will explain in a minute what does it mean. Okay, so going back to the scheme, so this is like a generic noise model, this lambda. Here it's like plotted that way that it affects all the qubits. But if you will have this this assumption that your noise affects groups of qubits, maybe not all of them, but like groups consisting of like some number of qubits of your device, then we'll show you that such a model can be characterized efficiently, learned efficiently, and we'll also try to convince you that it provides quite accurate information about the noise that affects your devices. Okay, so like the mathematical structure of the noise model that we are going to consider here in this talk is the following. So you'll take this like so you take your like matrix describing the whole noise, and you now write it as a tensor product of noise matrices affecting different qubits. So schematically now, like I don't have like a single lambda that like this lambda that affected all of the qubits. Now it has some more it has some further structure. So you can see, like, for example, I have like some lambda that affects just these 2 qubits here, and we will call qubits that are affected by such a lambda a cluster. Yeah, and there are like different clusters. We can have different clusters affecting a different number of qubits. And yeah, so this is the correlated readout noise model that we are going to consider in this talk. And now let me tell you like how do we proceed. So we want to characterize such a noise model. So this is our assumption that we can break this like that we can decompose the whole noise into those let's say different pieces affecting different clusters of qubits. So this we know from the beginning, and now we want to design a scheme that will allow us to characterize such a noise model. So what we do, so firstly we need to design some experiments, because like we want to run it on real quantum hardware, and we need to know what to do. So this first stage is like experiment design and implementation. So here we will kind of specify what kind of quantum circuits do we need to run on a quantum hardware to characterize this model. And we'll collect the measurement statistics. Then there will be like the data post-processing part. So we'll take those data gathered during experiments and we'll analyze them on a classical computer to reconstruct the noise model. And finally, we want to know whether this reconstruction that we have is kind of reasonable or not. Because, okay, we can, we can assume that this is the model that is like affecting our device, but in the end, this might not be true. So this third step is also important. We want to verify whether our procedure works and whether the model that we reconstructed is accurate or not, or to what extent the model can describe noise that affects the device that we are studying. Okay, and now I'm going to tell you about this first stage. So how do we design experiments for learning such a noise model? Okay, so you may know that like in quantum information, there's like a procedure known as quantum tomography that allows you to reconstruct like a unknown quantum state. And here we are using quantum detector tomography. So we don't want to characterize the state that is prepared by a device, but we want to characterize this readout process. And because like the readout process is done by detectors, so hence the name quantum detector tomography. So we want to characterize the detectors that perform measurements. But there's like one additional word here, is overlapping. And this means that we are not going to use the standard quantum detector tomography, but we need to do it like in a smarter way. And I will tell you why this is the case just in a minute. But this overlapping means that we are going to run this detector tomography in a parallel way, really. So this is like a parallelization of detector tomography. And we have some like statistical analysis that shows what is the scaling of this procedure. And the scaling means how many circuits do we need to run on our device to be able to reconstruct the noise model. And this is an important question because like we want to know whether this is feasible, like the characterization of a noise model is feasible or not. And this is like connected to the number of circuits that we need to implement. But also, if you are familiar with the current, let's say, state of the art, you need to pay for running circuits. And usually those like, the costs are calculated based on the number of circuits that you need to, that you want to run. So if you will need to implement like a lot of circuits, that means that you will probably need to pay a lot. So, and you need to know how much do you need to pay for characterization of your device. Yes, is there a question?
Yes, I have a question here. Can you maybe give an intuition, because here we want to reduce the noise of k qubits, but we are in a device with n qubits, right? So why there is an impact of this n qubits here? Because my initial intuition was that it shouldn't depend on n, but for some reason it depends on the logarithm of n. Okay. So could you, yes. Mm-hmm.
Yes, okay. So let me elaborate. So in the first step, we want to characterize this noise. We are not going to mitigate it, at least for now. So this is the first like clarification. Going to clarify.
Okay.
Yeah. So, and now what is this n and k? So maybe let me go back to, to this scheme. Like, as I said, like we work with a model that has like that is restricted to some groups of qubits, yeah? So we say that, for example, our, let's say those clusters, so the qubits that are jointly affected by noise, they can be formed from, let's say, 5 qubits at most. This is our assumption. but we do not know which 5 qubits are jointly affected by noise when we start characterizing our device. So this K tells us what is the maximal number of qubits that can be jointly affected by noise, but still we don't know which qubits will belong to such a cluster. And we need to find out this structure. So this structure needs to be learned. It's not fixed from the beginning. So it may be that like qubit number 1, 2, then 10th, and 15 belongs to a cluster, but we don't know that in the beginning. And this is the reason why this N appears there, because we need to characterize jointly all groups of qubits consisting out of K qubits.
Okay, I understand. Thanks.
In the many qubits, this is related to the question. In the many qubits, like number N, do you consider noise cancellation?
Okay, we are not speaking about noise cancellation or mitigation at that stage. We just want to characterize this noise. And N is like a total number of qubits of a device. So like Filip is going to show you results for this IBM device consisting of 127 qubits. And this would be N. And then K tells you what is the maximal number of qubits that can be jointly affected by noise.
So this talk is not, this consideration now is talking about localization of noise?
Yes, we want to find groups. We want to find like groups of qubits that are jointly affected by noise. Yes.
And within the group, there is no localization, no cancellation?
As for now, not, because we are just characterizing this noise. So we want to find out like a group of qubits that is jointly affected by noise. And then we can, if we know this, we can have some further consideration how to cancel that noise. But this is like a further step. The first thing to do is to characterize those groups. Is that clear now? Yeah. Oh, great. Okay. Maybe are there any further questions at this stage?
I don't see more questions now, so I think we can go on.
Okay. So this is like a theoretical result that tells you that basically the scaling of the number of circuits that needs to be run to characterize those groups of qubits jointly affected by noise, it is exponential in the number of qubits, the maximal number of qubits that we consider that belong to such a group, such a cluster, but is logarithmic in the total number of qubits of your device. And this is important. Whoops, where is the slide? Oops, I lost that slide, sorry. Oh, that's not good. Okay, sorry, so I will just tell you the numbers because one slide is missing here. So I wanted to give you some intuition about how does this work. So for a device that consists of 125 qubits, and let's say that we have a device that consists of 125 qubits, and this K is equal to 2. So we are kind of interested in characterizing noise affecting all pairs of qubits. So this is like a very basic task. So if you would run just this quantum detector tomography, not in a parallel way, but in the standard way, you will need to run around, I guess, 30,000 of circuits to do it. But if you do it in this smart parallel way, you just need 40 circuits. So this is like a huge reduction in the number of circuits that you need to run. And of course, this is like a more efficient way to do it, this overlapping way. So this really makes a difference. And now IBM gives you access to this like 127 qubits, sorry, but they said recently that they are 2 years, they hope to give access to like devices consisting of thousands of qubits. So this really will matter in the future, that how do you characterize your device? Because like the standard way will become simply infeasible to implement. Okay, so just now a bit of insight how does this overlapping tomography works. So we take our device and we prepare like all Pauli eigenstates in the beginning, and we measure them, and we get some measurement outcomes. Yeah, and from this measurement outcomes, we are going to reconstruct those mathematical, let's say, representations of measurement operators, so these POVMs, for those of you who know. But this is maybe not so important, but just to give you like a rough idea what's going on here. And basically, those measurement operators will describe a measurement process in which, in subsystem A, consisting of some number of qubits, some input state was prepared and some outcome was obtained. Whereas in the rest of the device, that is denoted by A bar here, there was some other input state, like a fixed input state, this row alpha, and all the results, measurement results, are forgotten. So this is kind of characterization of so this is the measurement process that we are able really to characterize with this overlapping, quantum overlapping tomography. And those mathematical objects that we reconstruct, they are the basis for the further analysis. So everything that we are going to present from now on really is based on those reduced POVM operators, this reconstructed POVM operators. Okay, so what kind of characteristics can we provide? And we are going to show them to you. So the very basic characteristic of this readout noise are the so-called correlation coefficients. So basically, those coefficients, they tell you what is the influence of the state of one qubit on the measurement results of the other qubit. So let's say that you take 2 qubits of your device. This is like the qubit I and this is the qubit J, let's say. And you study the measurement statistics on qubit I when this qubit J was prepared initially in, let's say, state 0 or state 1. And you will get like 2 probability distributions. State PI0 when this qubit J was in the state 0, and PI1 when this was in this state 1. And you can like verify how different those probability distributions are. So one way of doing this is like by calculating the total variational distance, and this gives you like some way of quantifying those correlations between 2 qubits. And these are, we call those like classical correlation coefficients, because like this state here, input state to the qubit J is really like a classical 0 or 1. But of course, you can generalize this and consider like the full like quantum correlation coefficients. And the only difference now is that here you consider 2 quantum states, rho and sigma, let's say. And you will get like another quantification of those correlations, but now they will take into account the fact that the initial state here can be like a quantum state. And Filip will tell you what are the differences between the two, like on real quantum devices. Okay, and like to just give you some intuition, what like those results are going to be presented in percent. So if we say that like a correlation coefficient is equal, let's say, to 10%, that means that this probability distributions on state I differ by 0.1 in this total variational distance when you change the state on the qubit J. Okay, and those correlation coefficients, there are also like a very basic quantity, because they characterize just like correlation between pair of qubits, but they are also quite important for our analysis. Because as I told you in the beginning, we are interested in characterizing these clusters, like the groups of qubits that are jointly affected by noise, but we do not know which qubits belong to a cluster. And in order to find out this cluster assignment, we run an algorithm that takes as an input those correlation coefficients, and by analyzing them, it outputs like a cluster assignment. So it tells us which qubits should belong to a group that is jointly affected by noise. And you may think that this is like a community detection problem in a sense. So you have like qubits, you have some characteristic of correlations between those qubits, and you like want to find like assignment that like all qubits that are correlated are in one group. But this is not how this works really, because here we do not want to form those clusters that consist of too many qubits. As I told you in the beginning, like the scaling of the procedure is exponential, and the maximal number of qubits belonging to a cluster. So we do not want to form like clusters that are too big, too large. So this is not really an algorithm that is used by like those algorithms, those like social media or social networks that try to assign people to very large groups. So it does not work like LinkedIn that propose you that maybe you should connect with this or that person, but we really need to have some constraints here. So we fix the maximal number of qubits that are allowed to be in a cluster. And then we run this algorithm. So this is like an optimization problem. So we fix the maximal number of qubits that can be in a cluster, and then we run this algorithm to find out this cluster structure. And I guess this is all that I have to say about this like first theoretical part of this talk. And now it's over to Filip to describe experiments. But maybe there are some questions to this first part.
Thanks. Thank you, Jan. Let me check our chart.
Well, the smallness of the cluster,
yes,
does it mean the localization of noise?
The cluster is like a group of qubits that are jointly affected by noise. So the size of the cluster is how many qubits we allow to be in such a group.
Yes, but is it related to the localization of noise?
Yes, so qubits, we say that qubits in the cluster are jointly affected by noise. Yeah, so they are like noise in the readout process of those qubits is correlated. And we kind of characterize all transition probabilities when it comes to the readout process, yeah.
So could I find an optimum by looking at the way a qubit belongs to a cluster that I don't know a priori, but can optimization tell me which is the best configuration to cluster?
So basically we use those like, first thing that we do, we characterize all pairwise correlations. And then we try to find like optimal cluster structure based on those pairwise correlations. So we want to like, whenever we find that two qubits are strongly correlated, and then maybe there is some other qubit that is strongly, let's say we fix this I and J, we know those two qubits are strongly correlated, and then maybe there is like some qubit J prime that's also correlated with I. So then we form cluster out of such pairs, yeah? And this is like a very basic understanding of this clustering algorithm.
Okay.
And yeah, but we also further verify this model. As I said, this is like the first step of our procedure is this verification. And this allows us to tell whether our kind of algorithm works well or not. And it turns out that this is quite accurate way of characterizing those clusters.
So very naively, can you define in one sentence the total variational distance?
Oh, yes. So you take two probability distributions.
Yes.
And you just kind of calculate the difference, like one by one. Like, let's say you form a vector. So you like subtract entries and take absolute value of those entries and then sum up this.
So this is similar to Kullback-Leiber?
For classical.
Well, I mean, it can be bounded in some directions by it, I suppose, but it's like this is like a proper distance in a sense of measure.
So it's different than Kullback-Leiber.
It's different, yes, but it's related to it.
Great, thank you.
Thank you. And just maybe to clarify what Janek was saying, that like this optimization that we do is like heuristic. We don't have like any guarantees. It's just something we came up with, and it seems it works in practice, but it's not like a rigorous thing, right?
Okay, very nice, thanks.
Okay, so I will stop sharing now.
Okay, do we have any more questions before Filip will take it over? No, so I think we can go on, and Filip, now is your turn.
Okay, super. You can see my screen, right?
Yes, I can see.
Great. Okay, so hello everyone. Yeah, I'm Filip. Thanks a lot, Janek, for talking about the first part. So it is my pleasure to continue with the experiments that we did. And those experiments were made on two systems of superconducting qubits. The first one was IBM's machine called Washington, and we did experiments on the 109 qubits. And the second one was Rigetti's device. It's called Aspen M1, and we did experiments on 55 qubits. So first graph with results is very simple. It shows just single qubit errors. So what you can see is a cumulative histogram. So on y-axis you have the fractions of all qubits in a device, and the n-axis shows the distance from ideal detector in percent. And now the green lines are for IBM's device, and blue lines for Rigetti's. There are basically two things that are important here. So first, in fact, there are two types of lines, and like solid lines are just classical errors, and dashed lines are quantum errors. And basically the difference between the two would suggest strong non-classical effects in noise. So like a little bit different noise model than just a classical one that Janek was mainly talking about. And well, I suspect that you cannot really see the difference. So in here, this is some indicator that classical noise model seems good when you only look at single qubit level. So those lines are like basically overlapping. There are very, very small spots when you can see difference between solid and dashed. And this will be somehow different in the next slide, where I consider 2-qubit measurements and correlations between them. But now the second thing to point out for this graph is that while the readout noise is significant, as Janek was trying to convince you at the first slide. So to just understand maybe what this means, these numbers mean physically. So basically, this is just a probability of getting outcome 0 if the input state was 1 in this case. So this can be as high as like 30–40%. And well, you can also compare the two devices and see that Rigetti is somehow, in general, a little bit worse than IBM's when it comes to magnitude of single qubit errors. And now let's go to the correlations. So the second graph with results shows correlation coefficients that Janek described earlier. So the x-axis is this coefficient in percent. This again basically tells you how much input state on 1 qubit affects the readout noise on the second qubit. Again, this is a cumulative histogram, so the y-axis is the fraction of all pairs in the device. And please notice here that y-axis starts at like 95% because a lot of correlations are very small, so we plot just this top part. And similar as previously, we have two colors for both devices, and they have both solid and dashed lines indicating like classical and quantum correlations that Janek was mentioning. So whether we consider quantum effects in this noise, or we can describe it just purely classically. And the situation is quite different than for single qubits, especially when you look at Rigetti's device. So it seems that non-classical effects are present in there, at least to some degree, when you look at two-body correlations. And when you look at the magnitude, most of the correlations are small, as I said. So for IBM, like even below the 0.5%. For most of them, but it can happen that they are very strong. So like around, for example, 20% here or 50 for Rigetti. And here you can see how those correlations look when plotted on a device's connectivity graph. So this is IBM's Washington. All connected qubits here are connected in the sense that you can perform 2-qubit gates between them. You can entangle them directly. We plot here only correlations above some threshold, so it is like well visible. Also here some qubits are faded. Those are the ones that we did not use for our experiments because they had too low single qubit gates fidelities, like those guys. So since we are doing this tomography of measurement noise, Janek mentioned that you need to prepare like Pauli eigenstates. You do this using only single qubit gates, and in order for the tomography to work, we need to assume that the single qubit gates are perfect. And for most of the qubits, indeed, the single qubit gates are very good, but sometimes they are faulty. So using them for measurement noise characterization would obscure the results. So in those experiments, particular experiments, we just did not measure those qubits, some of them. So left plot shows you correlations only between qubits that are neighbors on the device, while the right plot shows you, well, more of them. And basically the message here is that basically those correlations in readout noise do not need to correspond to the graph's connectivity of a device. So in this sense, they are geometrically non-local, but we can still easily detect them using this overlapping tomography. And the same graph for Rigetti with
we are looking
very similar structure. Yes?
Who decides about the structure of these plot graphs?
Yes, so the structure of the graph, how they are put on the device.
Yeah.
This is just like how they are connected on a chip, in a sense that you can perform entangling gates between them. So here you have like 0 and 1 are next to each other. So those neighbors, you can entangle them physically, okay, like directly. So this is like how the chips are constructed.
But there is alternative structure?
Sorry?
It's not the only structure possible, right?
Well, I mean, so this is like a specific device that we characterized. So, this is like, the actual, like a very specific single quantum computer that looks like that. Of course, in general, I mean, yes, that the graphs can be whatever engineers can do, but this is like a specific, like real life device.
Okay.
Mm-hmm. Thank you. Yes. And as you can see, for example, here, right? Like, I mean, this is completely different graph. This is for Rigetti. So they have this architecture that it doesn't look like, this, I don't know, like this, like a lot of squares, let's say, but they have rather like octagons in different places, right? So this is like another possibility of constructing those devices, and different companies, take different approaches, as you can see.
Philip, there is a question on our chat, if I can interrupt. There's a question from David. Just curious why qubit 41 and qubit 112 are correlated.
Well, that's of course a very good question, and I have no idea. So what we are doing is kind of like we can check all of this, check those correlations, tell people what's going on, but as of now, we do not know what is like the source of those correlations. So this is like a development of a tool that can tell you what's going on, but not really why. So as of now, we do not know.
Okay, thanks.
Thank you. Okay. Yeah. So and just another quick plot that points out to this same like geometric non-locality. The x-axis shows you a distance on a device's graph, so how many edges you need to travel from one qubit in pair to another qubit, and the x-axis shows you the correlation coefficient. And as you can see, this bunch of like quite strongly correlated qubits in a device, they are like neighbors. The distance is just 1, so they are next to each other. But for example, qubits in a pair corresponding to this coefficient are quite far away from each other, so and still quite correlated. And for smaller correlations of a few percent here in this regime, doesn't seem to be like any clear relation to the distance on a graph. All right, so this is this is abundant. Shouldn't be there. Excuse me. Okay, so we talked quite a lot about those correlations, and now it's perhaps time to see what all of this can be used for in practice. So as Janek already told you, the learning of noise models we consider here can be pictorially divided in 3 stages. First is experiment design and implementation, and in our case, it's this detector overlapping tomography experiments. Now data from those experiments has to be analyzed, this post-processing stage, and this post-processing is that we calculate these correlation coefficients. And as Janek mentioned, these correlation coefficients are an input to a heuristic optimization algorithm, which allows to get a cluster structure in readout noise. So this allows us to create a noise model that we can later use for things like error mitigation, for example. And finally, the final part of the workflow is to basically verify how good the noise model that we reconstructed fits the data, the experimental data. And those are the results that I would like to present now. So to verify the reconstructed noise model, we do benchmarks, which are fairly simple and in my opinion, quite natural. So we take a separable input state, put it inside a device, and then we measure energy of some local Hamiltonian. Local means that the terms in the Hamiltonian act only on some small numbers of qubits. So we estimate this energy, and then we basically can do 2 things. I mean, we can do many, but we do 2 things. First, we can simply compare predictions of the noise model with the results of experiments. This can tell us how well our model predicts energy estimation results on the device. So this is like just straightforward checking how well the noise model predictions agree with the data. And the second thing we can do, in my opinion, is a little bit more fun. So we can basically perform an error mitigation based on the reconstructed noise model. So we estimate this noisy energy, and then knowing the noise model, we use it to reduce the noise. And then we can compare it to the ideal energy that should be measured if there was no noise. So this benchmark kind of checks how well the error mitigation based on our noise model works in practice. And now before showing the results, I just want to explain why we decided to benchmark only separable states. Well, this is because we wish to investigate only the effects of readout noise. Therefore, we do not want to implement like complicated circuits, right? So separable states can be implemented with only single qubit gates, which are in practice very good. So basically, if something goes wrong in those experiments, it will almost exclusively be to the readout noise. Okay, so let's see the final plots of the presentation, the experimental results. So those are results of error mitigation for energy estimation of on 109 qubits from IBM. This is again a cumulative histogram. Now the y-axis is a fraction of implemented Hamiltonians, so we implemented like a few hundreds of them on different like separable states. On the x-axis, you see absolute energy error per qubit. So this is like a difference between what you theoretically should get and what you actually obtain in experiments with error mitigation. And then you divide this number by number of qubits to, well, have like a reasonable figure of merit that can be compared between systems of different sizes. You have like error per qubit. And there are 3 lines here. The red corresponds to raw data, so no error mitigation. Magenta corresponds, so this one corresponds to error mitigated results, but based on the uncorrelated noise model. So we assume that there are no correlations in readout noise between qubits. And this green line shows the results of error mitigation based on the correlated noise model that we reconstructed using this overlapping tomography. So first thing to point out is that without error mitigation, the errors are quite high, like up to 20% per qubit or something like that. This line corresponds to the median over Hamiltonians, so like this dashed black line. So then you can see that the mitigation based on the uncorrelated noise model works all right, like it does improve the results quite a lot. But also we see that using correlated noise model can improve them even further. So since it's not costly to do this, it seems that it's quite a good idea. And similar results for reget this device, where yeah, you also can see such improvements. Okay, so that's all. Just to summarize the presentation, what Janek and a little bit me talked about is like efficient learning of readout noise using detector overlapping tomography. We talked about measures of correlations that have some like operational meaning. What I mean by that is that they have some clear interpretation in terms of what they mean. We talked about like using the data from overlapping tomography, so those correlation coefficients to find noise models, cluster noise models, so where only some like small subsets of qubits are correlated with each other, not that everything is correlated with everything. And then we did present the results of noise model benchmarks with success on as big systems as 100 qubits. So if you'd like to learn more about this stuff, so this is a GitHub repository with some of the code that can implement parts of this. So it's not yet updated with the newest results, but we plan to work on that soon. And you can also check out the previous paper about this, which talks about parts of this stuff with this name. All right, and as Janek advertised previously, just like the quick advertisement, if you're interested in theoretical quantum computing and near-term stuff like error characterization or mitigation, there is a postdoc position open in the group of Michał Szmaniec so our group, and feel free to contact him using this email. Okay, that's all from me. Thank you.
Okay, great. Thank you, Filip. All right. So now it's time for questions. I can see one question or two questions on our chat. The first one is from David. For IBM with n equal to 109 qubits, what's the cluster size K with regarding error?
Yeah, so in there, most of the clusters were quite small. So we got like some of them were 3 qubits and some of them were 2 qubits. So like not that big.
Okay. All right.
But like the maximal size that we considered was 5, I guess. Yeah.
Right. Like so, I mean, we like yes, theoretically it could have been possible to see all of the 5 qubit clusters, but our like optimization told us that we don't need 5 qubits in this case. Yeah, sorry. Thanks.
Okay. All right. So David, I hope that it answers your question, but if you have any doubts, feel free to follow up. There is also a question if you can put the links in the chat, like a link to the group website, I believe, and also link to the code repository might be useful.
Sure.
I understand that the code is open source, right? So there's the open source.
Yes.
Okay, great, fantastic. Might be valuable for other researchers. And there's another question from Cayetano. Is this noise random or some kind of periodic noise? If it's random, then how can you establish the noise interaction among the qubits?
Yes, so that's a very good question indeed. As of now, we do know that this noise like changes in time. So in general, you cannot, just once characterize it and then use the same characterization a week later or something like that. So in general, we think that a good workflow would be to, like, at the stage of, all of those vendors, those people who make those quantum devices available, they do like a daily calibrations of those devices. So like to tweak everything. And then we think that a good workflow would be to just kind of like do this characterization on the calibration stage, and then use it for some finite amount of time, and then it should be like more or less stable. It's but it's an indeed kind of area of open research to see how stable the noise is in those devices. So to some degree it is stable, like in the sense that we did this calibration, and then I don't know, I did experiments like in few hours later or something like that, and those were like the results that you saw that were fine with error mitigation. So so to some there is some stability, but it's not clear yet how what are the timescales really. So this is something that we and people around the world would like to investigate. I don't know if this answers this question. Perhaps I should clarify something. Maybe I misunderstood.
All right. Cayetano, did it answer your question? If not, then you can also unmute yourself and follow up. Oh, Antonio said thank you, so I believe that this is fine.
Yeah.
All right. So yeah, if you could put this links to the chat, that would be perfect.
Yeah. I'll do it now in the meantime.
Okay, good. So in the meanwhile, let's maybe wait for more questions. Okay, thank you, Philip. So now we have the link to our code repository.
Yes, and also maybe to this paper I can put it.
Okay. Yes.
Just need to find it.
Might be helpful.
Okay.
Okay, great. Maybe you can also put
and
the
also
email.
Michał emails.
Yes,
right?
email address. Maybe someone will be interested in this postdoc position.
Sure.
In your group. Okay. So you started talking about some future plans, which is nice. Can you maybe also elaborate a bit more about some plans for the future research? Because I believe this might be also interesting for people considering this postdoc position, or maybe also some other similar topics in your research group.
Sure. Yes. So I mean, we both can answer this question. So like from we do quite a lot of stuff, I suppose, if about the strictly noise characterization and mitigation. So we probably would like to kind of push all of this a little bit further, like do some optimizations, improvements of the schemes of characterization, like to make it as much kind of user-friendly as possible, because we kind of with this repository we want this to be available to people to just use, and we want this to be efficient, so we want to improve everything, and we probably will be also investigating basically the error mitigation in more detail. Those are some specific examples of with this error mitigation. We did a specific methods we use for this, but there is a lot of stuff going on with error mitigation. So we are developing other methods for this that we didn't talk about here. Also of there's a lot of work in progress in trying to reduce the noise. So we are developing and testing new error mitigation methods and also existing methods, I suppose. So this I don't know if Janek, did I forget about something with noise stuff that we do?
Yeah, maybe our future plans, or mine future plans, are to, we were talking about readout noise, but there's also noise connected with gates. The point is that this noise can be correlated in time. So, the order of gates that you kind of apply to your state, it may matter what kind of noise affects such a circuit. So it would be also interesting to have like efficient characterization methods of this like noise that is correlated in time, because like people can characterize efficiently noise that is like a spatial. So like if you have a single layer of gates, for example, or if you have gates that are not like that are not correlated in time, that then people can do something. But as soon as this like correlations in time pop in, then the story becomes really complex and complicated. I think there's a lot of to be done there.
Yeah. I completely forgot about the noise in gates. So this, yes, we should also deal with that.
Okay, great. Thanks. Thank you. Do we have any more questions? I don't see more questions on our chat, but maybe someone would like to just unmute and ask. All right. I think that's all. So I don't see more questions. So let's thank our speakers once again. Thank you, Filip. Thank you, Jan. It was very interesting and informative and even inspiring presentation. So thank you. Let me maybe share my slides for the last time for today. So just some final words. Okay, so first of all, we would also like to thank all the participants for attending this meetup. Thank once again our strategic partners, NART and Cogit, for supporting us, and our honorary partners for helping us organizing this event. And it looks that the next meetup of the Warsaw Quantum Computing Group will be in October, so in the new academic year. So it will be episode 44. So stay tuned and you can follow our groups, profiles, fan pages, channels, Facebook, LinkedIn, Twitter, YouTube. You can join our mailing list. So let's stay in touch if you are interested. And what else? Thanks for joining today. Thanks for joining our previous meetings as well. I wish all of you a great summer, great holidays, and hope to see you again next time on our next meetings. So I will now stop sharing my slides and stop recording.